Okay, thanks, Karsten. First, let me start by just thanking the organizers, and John and Karsten and so on, for inviting me down so far. This has been a great meeting. It's the first time I've been to this. And I'm also learning a lot and picking up lots of pointers for lectures that I give at home and so on. So it's been really good. Just by way of introduction here, too, I'm not sure that everyone knows where Brock University is. It's a rather small university. We're located in the Niagara Peninsula, which is about an hour's drive south of Toronto, up in Canada. Okay, so just to get started here, so I think most of you probably are aware that EPR is magnetic resonance on unpaired electrons, and there are different ways that you can do EPR spectroscopy. And so the next two talks are divided into sort of two sections. Everything that I will talk about is sort of what we would place under maybe the heading of traditional EPR or old-fashioned EPR, if you like. The main difference being that we use continuous microwave radiation. So in all of what I'm talking about, there will be no pulses involved, and we'll be using a single microwave frequency and so on. And Stefan Stoll, who will be giving the next talk, will then take you on to the sort of more modern methods where we use microwave pulses and multiple frequencies. He'll talk about Endor and things like that. Okay, so the question is, why would we want to do magnetic resonance on unpaired electrons? What can we learn from these sorts of experiments? What can we study? So there are a relatively limited number of species that have unpaired electrons. So these are, of course, free radicals. What's important for this community, of course, are the transition metals, which have odd numbers of electrons, or if they're in a high spin configuration. We can also look at excited states of molecules that would otherwise be diamagnetic. So if you excite an electron into some higher orbital, then it's possible for the spins to flip. They're no longer a requirement that they be paired if they're sitting in different orbitals. And so, for example, you can create triplet states, excited triplet states, which can be observed by EPR. And I'll show you a little bit about that. What's really important, especially for bioinorganic EPR experiments, is that molecules where all of the electrons are paired have no magnetic moment and therefore no EPR spectrum. And this actually turns out to be both an advantage and disadvantage of the method. So on the one hand, it restricts us to this rather small group of species that we can look at. On the other hand, it can be really useful if we don't want to see part of our sample. And I'll show you that in a second. Okay, so we can use this, as I said, to advantage when we're looking at biological systems where there is some sort of active site. So usually in metalloproteins, we have a metal center, which is really where all the action is. It's the catalytic site in the enzyme and so on. And the metal is intimately involved in the function of the protein. And so usually there's redox chemistry going on. The metals are changing their oxidation states very often. And these, of course, as part of the function of the enzyme. And in many, many cases, the redox states are paramagnetic, where you perhaps have a high-spin iron or copper or something like this, which goes through a paramagnetic state. And so these can be measured using EPR spectroscopy. We can see these paramagnetic states. What's really important, though, is that there are no background signals from the rest of the system. We only see the paramagnetic species that's present. And so in the last talk, we heard that if we're going to use IR spectroscopy, for example, if we look at a protein, we have thousands of atoms and therefore thousands of vibrations and so on. And finding out what's happening at a catalytic site is difficult. You can do resonance Raman, of course, to pick out the site. You get that effect essentially for free in EPR because we only see the parts of the system which are paramagnetic. So if we're in the lucky situation where we have a protein where there's a paramagnetic center which is involved in the function, then EPR can be used to study exactly that catalytic site without worrying about all of the surroundings and the backgrounds which would otherwise interfere. All right, so here's a list of a bunch of proteins where EPR has been used extensively for studies. So a really big class of the iron sulfur proteins, right? So the ferredoxins so on. The heme and non-heme iron proteins, iron-nickel proteins, copper proteins. So there's a wide range here of species that we can study with this technique. Okay, so here's a sort of an outline of what I'm going to try and get through in the next hour and a half. I'm going to start by talking about just the basics of the EPR experiment, so how we actually do this experiment, what's the underlying physics of it, and along the way we'll bring in various interactions which influence EPR data. I'll also talk a fair bit about how the technicalities of doing the EPR experiment. The method is a little different than many other spectroscopic techniques. There are some peculiarities to EPR, and so I'll try to show you why those are necessary or how we do the experiments. And then we'll start talking about various different interactions which are important. A very important one is the hyperfine interaction. I'm going to introduce that by talking about solution NMR on small molecules, because it's easier to do that, but we'll immediately see that the situation in large protein samples is more complicated, largely because of the orientation dependence of the interactions. And so I'm going to talk a fair bit about the orientation dependence of the EPR spectra. So what happens if I change the orientation of a molecule in my spectrometer, how that influences the data, and show you how that plays a very important role when we're dealing with protein samples. And to illustrate that, I want to show you some data on single crystals that I was involved in analyzing quite a number of years ago, actually. But anyway, it's a nice illustration of what's known as the G anisotropy. And then we'll go on and talk about couplings between electrons and the concept of the zero field splitting. And I'll show you some data for triplet states and radical pairs, and then we'll move on to finally to high spin systems. So these are metals where we have spins which are greater than a half, so maybe 3 halves or 5 halves and this sort of thing. And we'll talk very briefly about a construct called a rhombogram, which is useful for analyzing these high spin spectra. Okay, so just by way of mentioning a few extra materials that are useful. So if your interest is piqued by this talk and there were some details that you maybe wanted to know more about, here are some references. There's a very nice textbook came out a couple of years ago by Hagen, which is called Biomolecular EPR Spectroscopy. This is, I think, very accessible to someone who's not really has a strong background in physics or so on. So a problem for many students in trying to get into understanding EPR is that there's an awful lot of physics involved in it, and if you're an inorganic chemist, you're probably not so comfortable with that. This is written in a way that is very accessible. For those of you who do like physics, there's Weil and Bolton. This is a really nice fundamental treatment of EPR with lots of mathematics and tensors and Hamiltonians and all that stuff, but is very thorough. And then I can make a plug for a chapter that John and I just finished writing, which is a nice, I think anyway, little introduction to EPR. And but anyway, a lot of this lecture is based on this chapter. Okay, so let's start at the beginning. So EPR, of course, we are measuring the magnetic properties of atoms. And we all know that if you have an electron or proton, it has spin angular momentum, which we can describe by a vector. And associated with that angular momentum is a magnetic moment. Right? And so in the case of the electron, the direction of the magnetic moment is opposite to that of the spin vector. And we have this relatively simple equation which relates the size, the magnitude of the magnetic moment to the spin quantum number s. And the proportionality factor here, so the square root of s into s plus 1 is just the length of the spin vector. And so the length of the magnetic moment or size of the magnetic moment is just related to that by this proportionality factor. There are two quantities there. One is beta E, sometimes written as mu E, which is the Bohr magneton. This is just a physical constant. and GE, which is the free electron G value, which is approximately 2. So while showing this picture, maybe I should also say a couple of words here. We very often represent electron spin in this way, right? So some kind of sphere representing the electron, and then a little arrow showing that it's undergoing some kind of spinning motion and has a magnetic moment. If that picture were correct, there would be no magnetic moment, right? So if I were to take a spherical charge distribution and spin it, I don't generate any magnetic moment. So this is a sort of a hand-waving classical representation of something much more complicated on a quantum mechanical level. It has to do with the structure of the actual particle of the electron and so on, which I don't want to go into. But it's important to realize that if you do take a spherical object, spherical distribution of charge, and were to just spin it, give it angular momentum, you wouldn't generate a magnetic moment. Okay, so anyway, we have this magnetic moment, and if we were to place the magnetic moment into, or this particle with a magnetic moment into a magnetic field, then the magnetic moment, or the spin vector, can align itself in two possible orientations, right? This goes back to the classic, or the Stern-Gerlach experiment, which I'm sure you all heard about in your undergraduate courses, that the direction of the spin vector, or the magnetic moment, is quantized in a magnetic field, and so we get two spin states with different orientations of the magnetic moment relative to the field. Right? And so here we have this quantum number ms, then can be either 1/2 or -1/2, and the energy separation between these two states in a magnetic field with strength B0 is just GE times beta E times the strength of the field. And so an EPR experiment, of course, is the absorption of electromagnetic radiation by a transition between these two states. And so you can calculate the relationship between the field and the frequency. So if I just divide through by h here, I'd get G beta E over, or GE beta E over h is 28 gigahertz per Tesla. So in other words, if I had a field of 1 Tesla, then the energy separation here in frequency units would be 28 gigahertz. Okay, so that, of course, is also very much the basis of NMR spectroscopy, which I think most of you will be fairly familiar with. But there, of course, we would be looking at the nuclear magnetic moment. And so the real fundamental difference between NMR spectroscopy and EPR spectroscopy is the size of the magnetic moment and the differences in the frequencies. Right? So the resonance frequency for an electron is about 600 times larger than that of a proton. So, for example, if we took a sort of small routine NMR spectrometer, which has a proton frequency of 300 megahertz, right? If we were to use that same magnet to do an EPR experiment, the frequency would be 180 gigahertz, right? So much, much higher frequency. If you convert that into wave numbers, that 180 gigahertz is about 6 wave numbers. So when we do EPR spectroscopy, we're working in the microwave region or in the far infrared, depending on the size of the magnet that we use. Right? The other thing which is very different in EPR from NMR is the fact that the couplings, the interactions of the electron with other electrons or with the nuclei and so on, or with, so with the interactions anyway involving the electrons, are generally quite a bit stronger than what you would observe in an NMR experiment. And so as a result of that, the spectra that we are measuring often are much, much broader. Right? So if you look at an NMR experiment, a very narrow one would be 1 hertz or less, and a broad solid-state NMR spectrum would be 100 kilohertz. In EPR, the widths of the spectrum, a narrow one would be 1 megahertz, and in extreme cases, you can have spectra which are several gigahertz wide. So the spectra in NMR or in EPR are much, much wider than they are in an NMR experiment. Okay, so there is also another really important difference between nuclear magnetic resonance and electron magnetic resonance, or EPR, And that's the fact that the electrons really have two types of motion that they're undergoing in an atom. Right? So we have the spin, of course, which I showed you before, but electrons also have orbital angular momentum. In this really oversimplified classical type picture, the electrons circulate in some way around the nucleus, and so there is also a magnetic moment associated with the orbital angular momentum L. Right? And so we have a completely analogous expression which relates the size of the magnetic moment arising from the orbital angular momentum and relating that to the orbital angular momentum quantum number. What's different here is that the proportionality factor is different for the spin and the orbital angular momentum. So for the orbital angular momentum, we have only beta as the proportionality. With the spin, we have this g times beta. So there are these two contributions then to the magnetic moment, and that is important for what we observe in an EPR experiment. So in general, of course, we have these two types of angular momentum, and what's important is of course, the total angular momentum is what will determine the total magnetic moment, which will interact with the magnetic field and give us our energy levels. So what we need to do here is actually calculate J, which is the total angular momentum and is the vector sum of S and L. And then our magnetic moment here will be some factor G now, which is not just the free electron value, but a G factor times beta E times this J quantum number. So if we're in a molecule, we heard this in one of the earlier lectures, the orbital angular momentum generally is quenched, or there's very little orbital angular momentum. So in molecules, generally the total angular momentum is very close to or very similar to the spin angular momentum. It's the major contribution. And so as a result, this factor G is very close to the G value that you would see for a free electron. Right? But having said that, there is some residual orbital angular momentum, usually, and so that we don't have, our G value here, our proportionality value, is not exactly the same as the free electron value. And the exact value that we see depends on how the orbital angular momentum and spin angular momentum couple together. Right? So we have spin-orbit coupling, which will be different in any given situation or in different molecules. And so the G value, the size of the magnetic moment, and therefore the frequency or field that I need to cause a transition between the spin levels, will vary from molecule to molecule as a result of the spin-orbit coupling. So down here are just two examples. So if I look at copper-2, if I just take copper ACAC and measure the G value there, we get a value of 2.13, so slightly higher than the free electron value. If you put titanium-3 ions into solid TiO2 and measure their G value, it's a little bit lower than the free electron value at 1.96. And so one of the main pieces of information that comes out of an EPR experiment are the G values here. And they give you or can be related to the spin-orbit coupling that's happening within the molecule. So understanding the G values can be quite complicated. The theory behind that is fairly involved and so on. And coming up with a really good explanation of why the G value for a particular species is what it is not always simple. But at a basic level, we can use the G values to identify different species. Right? So if we know from experience what the G values of a certain class of metals or radicals are, then if we have an unknown sample or some sample where we're looking at some certain effect, we can identify the resonances or frequencies coming from a particular species on the basis of the G value that we would observe. Okay, so the question then is, well, what set of conditions would we want to use for our EPR experiment? And so in general, in magnetic resonance, there's sort of a paradigm that says that the higher the frequency, the larger the field, the better. You wind up with better sensitivity usually, and the separation. So if we have two species with different G values, their signals will be separated more clearly if I'm at higher frequency. So there are a whole range of frequencies that are used for EPR. This is a rough list of commercially available spectrometers ranging from 1.2 gigahertz up to something in the range of 260 gigahertz. For technical reasons, the most common frequency that's used is 9.5 gigahertz. This provides a setup where the sample handling is easy, the equipment that you need is not outrageously expensive, and so forth. Right? So associated with each of these frequencies, or most of these frequencies, is a letter. And this is a frequency band. So these letters, the origin of them comes from the Second World War, when microwave technology was being used to develop radar and so on. And the military didn't want the enemy, I guess, to know what frequencies they were using and so on. And so they came up with a secret code to label each of the frequencies here. And so we still use this terminology today. It's a sort of an unfortunate remainder from, I guess, from this history. The letters here have absolutely no correlation with the with the frequencies at all. But if you read the literature of EPR spectroscopy, very often you will see a spectrum plotted, and in the caption it will say, this is the X-band EPR spectrum of whatever compound, and so on. And so what that means is that the frequency that was being used was around 9.5 gigahertz, within some range of maybe between about 9 and 10. Right? Fortunately, above, well, I don't know, somewhere above about 200 gigahertz, there are no letters used, and people just refer to that whole range as millimeter band and just give the frequency, which is probably better. Anyway, here are the corresponding fields that we need for a free electron. And so the field for 9.5 gigahertz is 0.34 Tesla, or 3,400 Gauss. This field can be generated quite easily in a relatively large electromagnet. If we go up in frequency to Q band, 34 gigahertz, this is 1.2 Tesla. This is about the limit of how far you can go with an electromagnet. And anything above Q band is done with superconducting magnets, and as we'll see in a few minutes, that presents a whole lot of really very serious technical issues. And so as a result of that, these higher frequency bands, so anything really above Q band, is usually referred to as high field or high frequency EPR, and the construction of these sorts of spectrometers is generally much more complicated and much more expensive than these lower frequencies here. Okay, so the basic idea of an EPR experiment is fairly simple. We have these two spin states. We put our sample in the magnet. The spin states split, and then we're going to try and observe the absorption of microwaves. And if we're using an X-band spectrometer, then we're going to use 9 gigahertz microwaves and try and measure that absorbance. So generally, the way that you would do that kind of experiment, I mean, if you're doing a absorption, UV visible absorption experiment, you would have your light source, you would have your sample in some kind of container, you have measure the intensity of light before it enters the container, you measure the intensity afterwards, and you can work out the absorbance of the sample. So it turns out that for EPR, the absorbance, the amount of absorbance that you are measuring is extremely small. And so doing the experiment in this way is really only feasible if you go to very, very high fields where you have a very large energy separation between the levels. And so if I tried to do an X-band experiment in this way, I would run into serious problems. I really can't measure the absorbance effectively doing things this way. So we use a different approach. Well, first of all, we should maybe mention a few reasons why that is, so why we have such a weak absorbance. So the first one is that we can look at the Boltzmann factor, just look at the population difference between the two spin states at some field, right? So if so here would be the Boltzmann factor. I can look at the difference in the population between the two spin states divided by the total population in them. That number turns out to be about 10 to the minus 3 for a magnetic field of 330 millitesla, or this would correspond to an X-band spectrometer. So we're trying to measure a very, very small population difference here because the energy separation is so small between the two levels. The other thing that can interfere with an experiment is spin relaxation. So if I'm doing a transition from one level to the other, the system has a certain propensity for that transition to happen spontaneously. So for the electron spin to flip from one orientation to the other as a result of just thermal energy and so on. If that process turns out to be very fast or fast enough, it can lead to very broad lines in our in the spectrums, and in many cases can make them so broad that you really can't observe them. On the other hand, if the relaxation is slow enough and we're pumping radiation into our sample, if the rate of the absorption is fast enough, you can wind up equalizing the population in the energy levels, and then your signal will drop. And this is known as power saturation. So we have all of these factors sort of conspiring against us to make the signals very weak and make the experiment somewhat difficult to do. So here's just a couple of diagrams to show you a little bit of how the behavior of the signal as a function of temperature and microwave power behaves. Those of you who do the practical on EPR will discuss this, so we'll look at the behavior of a signal as a function of the microwave power and so on. But anyway, if we plot 1 over t here, and so if we're decreasing the temperature as we move to the right in this scale, then just based on the Boltzmann factor, we should have this linear behavior. This is known as the Curie law, and the signal will get stronger as we go down in temperature. And so because of this, many, or most actually, EPR experiments are done at low temperature just to take advantage of the larger signal intensity that you get at lower temperature. However, if you continue down in temperature, usually you'll see behavior that looks something like this, where the signal tails off again as you go down lower in temperature as a result of the relaxation becoming slow, and you wind up saturating the signal down in this at lower temperatures here. So we can you can study the saturation behavior as a function of the microwave power. So the more power that you put into the sample, the more likely you are to saturate it. And so we can, if we measure the signal intensity divided by the square root of the power, you would plot that against this factor p over p1/2, the square root of that. We see that there's a region where changing the power doesn't really change the value of this quantity. So in other words, the intensity depends just directly on the square root of the power. But if we increase the power sufficiently, then the signal will drop off. And so if we can determine this p1/2 value, then we can know in which region we should work in order to be sure that we're not saturating our signal. Okay, but anyway, the bottom line or the upshot of all of that is that we have weak signals in EPR. And so to try and improve the sensitivity of our spectrometer, we use a resonant cavity to measure the signal. So rather than measuring the absorbance directly, we measure it indirectly using a resonant cavity. And so a resonant cavity for microwaves is basically just a metal box of some very exact dimensions, so that when we allow microwaves to enter this cavity, we can set up a standing wave. Right? So the microwave forms a a field. You can see here's one particular geometry. The blue lines here are the magnetic lines of force for the microwave field, and the red ones are the electric part of the electromagnetic wave. And so if we design our cavity properly, we can make sure that the magnetic lines of force are concentrated where our sample is, and the electric lines of force then are separated or in a different region of space than where our sample is. And this will allow the interaction between the magnetic part of the microwave, which is what causes the transition between the spin states, to be focused in our sample. Right? And there are lots of other possible designs. This is just one which is commonly used, but there are many, many other ones. And each of them has their own advantages and so on. I'm not going to go into any great detail here. Okay, so we have our resonant cavity with the sample sitting in the magnetic part of the microwave field. And so here's a picture actually of a resonator made by Brooker, the main producer of EPR spectrometers. You can see here at the back there's a metal tube. This is a waveguide. Microwaves are in a bit of a funny region of the electromagnetic spectrum. We can't transmit them easily through a cable. The impedance is much too high. On the other hand, if you try to transmit them through free space, they diverge very broadly. There's a lot of divergence. But if you use a waveguide, which is basically a metal tube, then it's easy to transport them to the resonator. In any case, we have our resonator, our metal cavity. The sample would be sitting inside here. We bring the microwaves down into the cavity. And we want to set up this resonant or standing wave within the resonator. And we couple the microwaves into the resonator using a slit. So this plate here that we're looking at would be at the back of the resonator, at the place where the waveguide meets it. And we put a slit there that allows the microwave to pass into the resonator. And then there's a small screw here which has on the end of it a metal plate which couples the microwave into the resonator. And so a big part of any EPR experiment is to adjust the coupling by adjusting this iris to couple the resonator properly with the microwave source. So when you do that, if you take set the spectrometer up so that the frequency is being swept through some fairly narrow range, then as we adjust the screw up and down, we would first of all see that we have, what we would be measuring in our experiment is the reflected power, so the power being reflected back from the resonator. Then what we would see is that we have some relatively high reflected power, but there's a particular frequency in the middle of this range where the reflective power drops fairly substantially. And this is the resonance frequency of the resonator. And if we adjust our coupling screw, we can reach this situation where the resonator is said to be critically coupled to the source. And what this means is that at the resonance frequency, there is no reflected power coming back from the resonator. It means all of the microwaves being put in are essentially being absorbed in the resonator, and there's no reflected power. And if we adjust our coupling screw a little bit, then we can go to this overcoupled region where the resonance is broader and there is some reflected power. Or if we're undercoupled, then the resonance is narrower, but there is also reflected power. So the idea here, though, is that we're now going to lock our spectrometer at exactly this frequency where there is no reflected power coming back from the resonator. Right? And so if we sit right at that position, locked on this resonance frequency where there's no reflected power, and then we find ourselves in a situation where an EPR transition can occur within the sample, then the resonance in the resonator gets disturbed very slightly. So if we've coupled this thing where we're not in resonance with a transition in the sample, and then we change our conditions such that we are now observing a transition, or a transition is occurring between the spin states, it means that the resonance in the resonator gets disturbed a little bit, and we get some power now being reflected from the resonator. And the thing that's important here is that the amount of power that gets reflected is greater than the amount that gets absorbed by your sample. So if we try to measure the absorbance directly, we would be measuring a very, very small change in intensity. If we do things this way, indirectly, and measure the reflected power, we get a much bigger signal. And so the resonator is acting essentially like an amplifier and amplifying the signal that we're seeing. Okay, so here's a schematic diagram of an EPR spectrometer. We have our microwave source. We would take the microwaves out, have an attenuator that allows us to adjust the power so that we can avoid saturation if we need to. There's a device called a circulator which will allow microwaves to pass from an entrance slit here. If they're moving in this direction, then the microwaves will be allowed through, and they will exit through a port here. If a microwave coming back from the resonator down here enters the circulator, it gets passed through to the next port over here and will arrive at our detector. Right? And so in this way, we can see the reflected power coming back from our resonator. In addition, we build in a reference arm. So we take part of the microwave power here and shunt it over through this path. And we put in a phase shifter so we can adjust the phase of the microwaves, so move them back and forth. And that means that at our detector, then, we can also measure the phase of the signal relative to this reference arm. Anyway, the signal is then passed into a preamplifier, and we can then dump it into a computer or whatever other device we want to use and analyze the signals. What's also in this diagram is this so-called lock-in amplifier, and we've written down here 100 kilohertz modulation. And this is an additional detection method that I want to talk about now. So, yeah, actually I have a couple of other things that I need to put in between here, which I had forgotten about. Anyway, so here's a picture of a sort of a standard spectrometer operating on the principles that I just showed you. What's important here is that if we look at our resonator that I just showed you diagrams for, the width of the resonance that we're using in frequency units is maybe on the order of 1 or 10 megahertz or so, something in that kind of ballpark. But our spectral width can be up to several gigahertz wide, so is usually much, much wider than the width of the resonance. So this means that the upshot of that is that we can't run our experiment by changing the microwave frequency. If we start changing the microwave frequency to match the spacing between our energy levels, very quickly we'll be way outside the resonance of our resonator. Right? So because of that, what we do is we vary the magnetic field. Right? And so if you're using an electromagnet, that's easy. You just change the current running through the coils in the electromagnet, and the field changes, and so we can can look for the resonance that way. Right? So, so the experiment is done then by varying the magnetic field. So in a typical absorption experiment, we would take the wavelength or the frequency of our light and sweep it and find the places where it absorbs. In this experiment, we do things the other way around, and we take the energy levels that we're trying to measure the transitions between, and we move them up and down until they match the microwaves that we're using. Okay, so but in our on the previous slide, I said we use this lock-in detection. There was something about 100 kilohertz modulation and so on. So even if we're using a resonator, we still have to struggle with weak signals in EPR. And so we use a different detection method. And this is a really, really important method for enhancing signal to noise in any kind of an experiment, and is used actually often in optical spectroscopy as well. And the idea here is that we take our signal and we make it vary in a way that we know. Right? So we sort of encode our signal with a pattern that we can recognize. And then when we measure the signal, we throw away any components that aren't behaving in the right way. So the way this is done in an EPR experiment is that we put extra coils on the side of the resonator. So just a few windings of copper wire on the edge of the resonator. which creates an additional magnetic field, a very small one, which is added on top of the main field that we're using for our big magnet. And then we make this extra field oscillate with a known frequency, usually 100 kilohertz. And so if this is our absorption line that we're trying to measure, right? So if there's some little bit of broadening and so on, if we apply our main magnetic field at different values, and then on top of it we have this small green modulation field, if I'm sitting here and the field is oscillating back and forth between these two values, then the signal that I measure will oscillate up and down between here and here. On the other hand, if I'm over there, then it will oscillate up and down with this higher value. And so you can see that if I can measure the height of this oscillating signal, then I can measure it provides me with a different way of measuring the absorption line. So what's important here, though, is that if I know that my signal now is oscillating with this particular frequency, I can put a filter on the amplifier and only amplify components that are oscillating with this frequency. And it means that I can throw away a huge portion of the noise in my experiment and really dramatically increase the signal to noise, increase the sensitivity of the spectrometer. And this can be used in all sorts of different variations. We don't actually have to use an oscillating signal. That's always used in EPR, but there are examples in other forms of spectroscopy where this pattern is something different. And as long as we know what the pattern of the signal is, then we can amplify only the components of the signal that have the right behavior. Okay, so as a result of this detection technique, though, what you can see is that my biggest signal will occur where the slope of my original signal is largest, right? So where the difference here, so if I look here, I've got a very large signal because the the red curve here varies by a large amount between here and here. So if I move the field by a small amount, the signal intensity changes by a large amount. And so if I plot the intensity of this peak, what I get is the first derivative of my line shape, right? And so the blue curve here is what I would measure in an experiment, right? And so in EPR, we always detect, or at least in this form of EPR, we always detect the first derivative of the actual absorption signal. Right? So there are a couple of drawbacks to doing that. The first one, of course, is that what you get is the first derivative of the signal and not the actual signal that you would like to see. You could, of course, numerically integrate it and so on. But the other issue that you come up against is that the amplitude of the signal and its shape both depend on the amplitude of the oscillating field, right? So here you can see these are some spectral data that I measured a week ago or so on a standard sample. If I start increasing the amplitude of my modulation, my signal here will get bigger and bigger and bigger, right? And so the conditions under which I do the experiment determine to some extent the amplitude of my signal, right? And that really you would like not to be the case in a spectroscopic experiment. More importantly, though, if I make the amplitude too large, then the width of my spectrum will start to change, right? And this can be a real problem if you've got a sample in which you've got signals of different line widths. If you have a narrow signal and a broad one, the question is then, what do I choose for the amplitude of my modulation so that I get as big a signal as possible without distorting it, right? And so this is just a detail that makes the method a little bit more complicated. The advantages are, though, the main one being that we get much, much better signal to noise, and we actually need this technique more or less anyway to make the experiment, feasible or practical. The other thing is, though, that having the first derivative is not always a bad thing. So if I have a line shape like this that has a little bit of structure in it, some shoulders and stuff, if I take the first derivative of that, I get this, and the features in the spectrum are much, much easier to see. Right? So if I'm looking for structure in my spectrum, then having the first derivative can be an advantage. Okay, so if that was the whole of the experiment, it probably wouldn't be all that interesting. If all we could measure was just the position where this transition occurs, we might learn a little bit about the spin-orbit coupling in our sample or be able to use it to detect the presence of some paramagnetic species. But the thing that really makes EPR useful is the additional interactions which the spins can undergo. So this is interactions between different types of magnetic particles and the spin-orbit coupling, which we'll talk about in a bit. So if I have magnetic nuclei, right? So most samples will have protons in them, if they're, some maybe nitrogens and so on. Then the magnetic moment of the electron, of course, will interact with the magnetic moment of the other particles, so with the nuclei. And this interaction is known as the hyperfine interaction. If I have a nucleus, a nitrogen nucleus, its spin is 1, right? And so what happens to our energy level diagram now is that up here I would have one of the two spin states, so the S equals plus 1/2, and down here S equals minus 1/2, so the two possible orientations of the electron spin. But each of those levels now gets split into two I plus 1 levels. So if I is 1 here, then I have 3 levels with m sub I, the quantum number m sub I, being minus 1, 0, or plus 1. And the same thing down here. And then if I look at where the possible transitions are, so if I leave the nuclear spin the same, then I can do a transition from the plus 1 level down here to plus 1 up there, from 0 to 0, and 1 to minus 1. And so I get 3 lines. And you can see that they appear at different magnetic field strengths, right? And the separation between them in magnetic field would be this quantity A, which is the hyperfine coupling constant. So what I would see then, if I had say a free radical in solution where I just had my unpaired electron and there was some single nucleus nearby that it was coupled to, if that nucleus was a proton, then my spectrum would split into 2 lines with a separation A. If it was a spin 1, I would get 3 lines, and so on. And so depending on what the spin of the nucleus is, I get 2 times I plus 1, where I is the spin of the nucleus. So of course, in any real sample, I don't just have one nucleus, but I have a whole number of them. And so if I have a group of equivalent nuclei, so for example, if I have a methyl group where the 3 protons are all chemically equivalent, then I would get 2 times n, where n is the number of nuclei, times I plus 1 as the number of lines, right? And then if I have a whole bunch of different nuclei, some of them in equivalent groups and so on, I would have the product of 2 times n times I plus 1 for one group of nuclei times 2ni plus 1 for the next group of nuclei, and so on, right? And so this number can become really large very, very quickly, right? So even for small molecules, the number of lines in an EPR experiment, at least theoretically, is very, very large. So what saves us in some cases is that the hyperfine coupling constants to many of the nuclei are very small and are not resolved in the spectrum. But in general, we can expect to see many lines in the spectrum. So just as an example, here is a verdazyl radical. This is a stable radical. It's a relatively small molecule. We have 4 nitrogens and 6 protons. Its spectrum here, you can see, has really quite a large number of lines. There's a lot of structure here. Getting the hyperfine couplings out, even for a simple molecule like this, is quite complicated. And we typically would have to calculate the spectrum and adjust the hyperfine coupling constants until the calculated spectrum and the experimental one match to get the values out. So here's a little plug for a tool that our next speaker, Stefan Stahl, has developed. This is called Easy Spin. This is a little toolbox for MATLAB that is really, really useful, very, very, very nice piece of software for doing these kinds of simulations. And so if you're doing an EPR experiment and want to simulate the spectrum, I would strongly recommend using that. That will handle almost any spectrum you would be likely to measure. Here's the URL to the website for that. There's lots of nice documentation, and Stefan is also very free with his time and will answer questions and so on, so this is very good. All right, so anyway, so this is a small molecule in solution. We get a spectrum like this, and we can simulate the spectrum, get out the hyperfine couplings if we're lucky. So once we've got those couplings, we'd like to interpret them in some way. So the main term for the hyperfine coupling is this so-called Fermi contact term. What's important here is that it depends on the electron spin density at the particular nucleus that we're looking at. Right? So we can see here, at least qualitatively, what the distribution of the unpaired electron in our molecule is like. We can see which atoms in the molecule are located where the orbital, for example, has lots of density, or places where there's very low density. You would see small couplings and so on. There is an additional term here which comes from the dipole-dipole coupling between the electron and the nucleus. What's important here is that it depends on orientation. You can see there's an angle theta here, and on the distance between the unpaired electron and the nucleus. If we're looking at a molecule in solution, this term averages to 0, right? So if I do this average over all the possible positions of the electron and possible orientations of the molecule, this term here will go to 0. Okay, so anyway, so for when we're in solution, this would be the main term that we would obtain, and we can use that to learn something about the distribution of the molecule, or the electron in the unpaired electron in the molecule. So for us, though, as bioinorganic chemists, what we're interested in, of course, are proteins. And these are very large molecules, and even in solution, very often, the motion of a protein is slow. Right? And so this averaging that I just talked about, which leads to the this dipolar term disappearing, would then need to be taken into account. So this is the one problem, that the motion is usually is very slow. The other thing, though, that can really interfere is the fact that the number of hyperfine couplings that are possible is usually extremely large. Right? And so rather than having nice, sharp lines in our spectrum, we get some kind of broad shape where we don't really see much of the hyperfine coupling. And then, in addition, if we've got a metal which has more than one unpaired electron, or a spin greater than 1/2, then we can have what's known as zero field splitting. And what's really important here is that all of these interactions are orientation dependent. They depend on how the molecule you're looking at is oriented relative to the magnetic field that you've applied. Right? So that means in a typical sample where I have some kind of random distribution, if I take a solution, I'm going to have all possible orientations of my molecules. And that means that for each molecule in my sample, I'm going to have a different value for my hyperfine couplings and for my G value and this zero field splitting and so on. So the orientation dependence is really, really important for protein NMR or EPR. Okay, so just to give you some idea how that works, if we're in the very fortunate situation where we have a single crystal of our sample, right? So if we've managed to take our protein and crystallize it and get a really good single crystal, then we can actually measure this orientation dependence by mounting the crystal onto some kind of a rod known as a goniometer, so that we can put the crystal in a predefined orientation in the field. And then you can change that orientation, right? So we would have some angle theta between some particular crystal axis and the magnetic field, and then you can measure the spectrum at different values of this angle theta. So if you do that, then you might get a set of spectrum that would look like this. Here's a bunch of different rotation angles. Here's our spectrum as a function of magnetic field, and we would get some pattern of lines that change as I rotate my crystal. I would then take those spectra, and for each orientation, I would record the positions of the lines in the spectrum, and then write those or convert those values, those positions, into an effective G value. So take the field and the frequency that I've done the experiment at and calculate the value G from those two quantities. And I can plot, in fact, G squared against the rotation angle as a plot. And what you will see is that the positions of the lines vary in this sort of sinusoidal or cosine type function. It turns out that the positions of the lines will always follow this particular function, so a term in cosine squared, cosine times sine, and sine squared. The coefficients of these are labeled GAA, GAB, GBB, where A and B refer to the crystal axes of the axes of the crystal. Right? So if I repeat this experiment and rotate about 3 independent planes of the crystal, or take 3 planes which are independent of one another, then I wind up with these 6 independent values, or G values. Right? I can then arrange those as in a matrix, so this is known as the G tensor, and then I would transform this tensor, this matrix, essentially by rotating the axis system that I'm using such that it's diagonal. When I've done that, these 3 values that I wind up with are known as the principal G values of the system. And these are not dependent on the orientation essentially anymore. These are properties of the molecule itself. Right? So the values here depend on the definitions of the axes A, B, and C, and so on. I could choose a different set of axes A, B, and C, and I would get a different matrix here. But there is only one set of principal axes, and these 3 values, GXX, GYY, and GZZ, these are properties of the molecule. So the transformation from here to here is done by multiplying by this, this is called a unitary transformation. This U here is a matrix. The elements of the matrix tell me the orientation of these principal axes of the G tensor relative to the crystal axis system. So just to give you an example of how you can use this is photosystem 1. We heard a little bit about the reaction centers and so on yesterday in Les Dutton's talk. So in the photosystem 1, there are iron-sulfur clusters, which are relatively easy to reduce, actually at low temperature, simply by shining light on the sample after freezing it in the dark. And so a number of years ago, we investigated a single crystal of photosystem 1. And so here's a spectrum taken at a particular orientation where the C-axis of the crystal was parallel to the magnetic field. And you can see there are essentially 2 lines in the spectrum. There's actually an additional peak here, which is labeled P700, which comes from this chlorophyll. But there's a big line here, which is this cluster FA, and then there's another one which is sort of buried underneath the P700, which is from FB. Then if we rotate the crystal, you can see that the spectrum changes really dramatically, and we get a whole series of lines. And there are, in fact, 6 lines that we can assign to A and 6 to B. And this is because in the unit cell of this crystal, there are 6 different possible orientations so 6 different molecules with different orientations of FA and FB. Right? And we can continue that game, go to a different orientation, and the lines all move and so on. And here we've gone now through 90 degrees rotation. So if we take all of those data, then we get this rather complicated-looking set of rotation patterns. But we took these through the analysis that I just told you about. From each of these curves, we get a set of G values. We can set them up into this matrix and diagonalize it and so on and get out basically 2 sets of information. So the first one is that we get the principal G values for each of these clusters. So we can measure the G values for these 3 orientations. But more importantly, we also get the angles between each of the axes corresponding to X, Y, and Z relative to the crystal axes. And then if we have the structure of the crystal, we can relate those to actually the structure of the cluster. And so it turns out here that the axes X, Y, and Z are arranged in this way relative to the iron-sulfur cluster. And then we can start by understanding how the spin-orbit coupling in an iron-sulfur cluster works. You can use that to, in fact, assign two of the atoms in this reduced iron-sulfur cluster to a mixed iron-2, iron-3 pair, and the other two being an equal valence iron-3, iron-3 pair. So we can use this to try to understand the electronic structure of the cluster. Okay, so when we're talking about the parameters that we get out of an EPR experiment, most of them are tensorial in nature, and there's some terms that we use to talk about them, the symmetry. So if I have a tensor component, this could be a hyperfine coupling, it could be the G tensor, it could be the zero field splitting. If all three elements are equal, then I would talk about a molecule or an interaction which is isotropic. And this will occur if I have tetrahedral or higher symmetry in my system. On the other hand, if I have a situation where two of the elements are equal and the third one is different, so here are two possible examples, then the symmetry or the interaction is said to be axial. And this will occur when we have a threefold or higher rotation axis in the molecule. And then if all three values are different, we would say the interaction is rhombic. And that occurs if the highest rotation symmetry in the molecule is only twofold, right, or lower. Right? So if we have either no rotation symmetry or only twofold rotation, then we would have a rhombic interaction. Okay, so you can do all this nice analysis if you have a single crystal, but it's pretty rare to have a single crystal of a bioinorganic sample. And generally, we've got a solution of a protein that we're interested in, and we've just spent months isolating this precious little bit of material, and crystallizing it is just not feasible. So almost all EPR spectra that you will see are taken on random distributions of orientations, and we get what's known as a powder spectrum. Even if the sample is not actually a powder, it's the spectrum that you would see if you have a random distribution of orientations like you would have in a powder. So if I have an isotropic G tensor, then all of the three G values are the same, and I just get a single line in my spectrum, and I can measure the isotropic G value. If, on the other hand, I have axial symmetry, then I have two different principal G values. One of them we would usually label G parallel, and the other one G perpendicular. If G parallel is larger than G perpendicular, then you get this pattern. And if it's the other way around, where G parallel is smaller than G perpendicular, then you would see this pattern. And then if I have lower symmetry, I would get a rhombic pattern, which looks like this. Right? So where I can measure the three principal values. So even if I don't have a crystal, I can get the principal values of my G tensor out from the spectrum. Okay, so I can measure those values. The question then is, how do I interpret them? So the interpretation, it turns out, is relatively complicated, and I'm not going to go through very much of it. I'm just going to leave it by saying that it depends on the spin-orbit coupling. And probably the easiest treatment is to use a perturbation theory treatment in which we treat the spin-orbit interaction as a small perturbation. And then if I can do a sum over essentially all of the possible orbitals in the system and look at the effect of the orbital angular momentum operator and so on. And you can do this kind of analysis for example, transition metals in different geometries, so in a tetrahedral or octahedral field and so forth, use a ligand field theory model. And what you will get then is a G value, which is the free electron value, plus or minus some term which contains this parameter, which is the strength of the spin-orbit coupling, and then a second term which will come from all of this sum. If we use crystal field theory, then this whole sum here would give us basically some number times the crystal field splitting. Right? And so you can qualitatively, you can sometimes understand the nature of the G values using this. Okay, so Without going into any detail, though, there's some general trends that you can see in the G anisotropy. So the first one is that if I have a radical with light elements like carbon and hydrogen, nitrogen, and so on, the spin-orbit coupling is weak, and the mixing of the orbitals by the spin-orbit coupling operator is a very, very small perturbation. And so they have very small G anisotropy, and the signals appear near G equals 2.0023. On the other hand, if I have a transition metal, it depends on which metal I'm looking at and so on, but the spin-orbit coupling is typically smaller or stronger. This is partly because the spacing between the d orbitals is very small, right, in comparison to the spacing between the sigma and pi orbitals in a molecule, which is larger. But the upshot of it is that we get larger G anisotropy from transition metals in general. Right? And so how big it is and what the form of it is, it depends on the electronic configuration, the symmetry of the ligand field, and so forth. But as a general rule, then, I can distinguish radicals relatively easily from metal ions in an EPR experiment because the radicals will all be appearing near the free electron value, and the transition metals will typically have broader spectra and be shifted away to a larger extent from the free electron value. Okay, so here, just to illustrate that, is some spectra that I got from a paper which came out quite a number of years ago on the chlorophyll cofactor P700, measured at different fields and microwave frequencies. And so this is a chlorophyll radical. There's a magnesium in it, but there are no paramagnetic metals present. So the main elements involved in here are carbon and hydrogen, oxygen, nitrogen, and so on. And so you can see if you look at the G values, the 3, X, Y, and Z values, they're all really, really close to 2.0023, a really small deviation from that. And in order to see that difference, we have to go up to frequencies like 300 or 400 gigahertz. And these types of measurements are really only possible in very, very specialized spectrometers. So this was done at the National Magnet Lab in Tallahassee in Florida, where they have these massive magnets that are not generally available to the general public. And so if I use an X-band spectrometer, which you will find in, typically in a chemistry department, then you will never see this difference, and you just get a single line in your EPR spectrum. If you compare that to the iron-sulfur clusters, which I just told you about, so this is what a photosystem 1 sample would look like if I don't have a single crystal, but just a solution which I've frozen, then you can see that I can resolve very nicely the 3 components for FA, and then if we look a little bit closer, the ones with the stars here are for the FB, which are a little bit buried, but you can pick them out relatively well as well. Right? And so the reason for that, of course, is that the spin-orbit coupling is stronger within an iron-sulfur cluster than it is within an organic species like the chlorophyll. Right? So which spectrometer you need depends on what you're looking at. And for metals, fortunately, X-band is usually good enough to resolve the anisotropy. For organic radicals, depends on which radical you're looking at. In some cases, like for P700, you have to go to really extreme fields to get the anisotropy out. Okay, so I'm going to move on now and start talking about systems with spins greater than 1. Right? So if I have greater than a half. Right? So if I have more than one unpaired electron, so I've got S greater than a half, if I'm looking at the total spin, then even in the absence of a magnetic field, so if I take my system at 0 magnetic field, the spin states are split, even though there is no applied external field. So if I have a spin equals 1, then I see, depending, of course, on the symmetry, but if I have rhombic symmetry, then I would see 3 levels split from one another. If I have, say, a spin 3 halves, then the ms equals plus minus 3 halves or 1/2 levels are also split relative to each other. And this is known as a zero field splitting, and it has a really big impact on the EPR spectrum of species like this. So the way that we describe the zero field splitting, so I'm not going to go through the quantum mechanics of it in any great detail, but if you were to write down the Hamiltonian for this interaction, it appears as a term which looks like this, where S here is the spin operator in matrix form, and then there's this matrix D which describes the interaction. Okay? And so if I set this matrix up in its principal axis system, it would look like this. So I would have diagonal elements, and the diagonal elements can be written in terms of two parameters, D and E. So this is the notation here is a bit unfortunate. We use D for the whole matrix. We also use D for a parameter which is an element of the matrix and so on. But in any case, for most practical purposes, these two parameters are what we use, the D and E, which is what we use to describe the zero field splitting. So the origin of the zero field splitting is there's really two contributions to it. There is the dipole-dipole interaction between the two or more unpaired electrons in the system. The spin-orbit coupling also will mix the spin states with higher states as well and cause this splitting. If we can ignore the spin-orbit coupling contribution, and that's a big if, but there are molecules where that's the case. So if that's the case, then we can relate the parameters D and E to basically to the distance between the electrons in the molecule. And so we have these two terms here, which have this average, which is an average over all possible positions of the electrons. R here is the distance between them, and then the X, Y, and Z are components of the vector joining the two electrons. And then we would have to do an average over all possible positions of the unpaired electrons. So if I were to take this to a little bit of an extreme and put my two electrons on different molecules now, and so I would have in that case a radical pair, then if I do that, then the distance between the two unpaired electrons is approximately the Z component of the vector joining the two electrons. And so if I make that approximation, then the parameters simplify quite dramatically. And our parameter D, now this average, just becomes 1 over the average of the cube of the distance. And our parameter E goes to 0. And so this is actually a really useful result because we can use that to measure distances between unpaired electrons within, sitting on different radicals. So I'm not going to talk about this, but we may hear some in the next talk a little bit about this, that we can put stable radicals onto proteins in different locations, and then if we can measure this parameter D, then we can get the distance between them, and you can use that to start to piece together the geometry of the molecule, of the protein, or we can look at conformational changes and so on if we see differences in the parameter D. Okay, so in terms of these different types of symmetry that we can have, if we have an isotropic system, then both D and E are 0. Regardless of whether they're present or not, if our system has very high symmetry, then this interaction would not be present. If we have axial symmetry, it means our D value will be different from 0, but E will be equal to 0. And for a rhombic system, both D and E are non-zero. So we can use the ratio of the parameters D and E then as a measure of sort of how rhombic the system is. Right? So if our E over D value is very small, then you can say, well, even if our system is not completely axial, it's close to being axial. On the other hand, the maximum value for this ratio turns out to be 1/3, and so if we have a value of E over D which is 1/3, then we can say the system is very, very rhombic, has no axial symmetry at all, and is completely rhombic. Right? And the value, of course, can vary, and it depends on the symmetry of the system that we're looking at. Okay, so the question is, what does this do to our EPR levels? So if I have the simplest case, which is for a spin 1, then this is what the energy level diagram would look like for a system with zero field splitting. So our spin levels, the +1 and -1, deviate from each other when we apply the magnetic field. The ms equals 0 level is unaffected by the field. And we get two transitions now. Because of the zero field splitting, because these levels start at a different value, then the positions of these two lines are not the same. Right? And so our spectrum then would get split into a pair of lines where the separation between them is related to the zero field splitting. And then if we take a random distribution of orientations, right? So this, the separation between these two lines will depend on which orientation the molecule is in, because our zero field splitting is orientation dependent. So if we do that and we were to use field modulation detection, then we would get a spectrum like this, where we see features from, which are the widest features here separated by 2D, for molecules in which the z-axis is parallel to the field, and then when y is parallel to the field, we get a splitting of d plus E, and when the x-axis is parallel to the field, it will be d minus E. And so from the spectrum, then you can measure the values of D and E. So that's the situation for a triplet state, and if we were looking at an organic molecule and wanting to measure its triplet state, the way to access that is to excite the molecule into a photoexcited state. And the lifetime of an excited triplet state is, depends on the molecule, of course, and the conditions, but typically is in the order of microseconds, maybe out to a millisecond if you're lucky. And so that means that I don't have nearly enough time to actually measure the spectrum. And so to get around that, we can do transient EPR, in which we now fix the magnetic field at some particular value, flash the sample with a laser pulse, and watch the signal decay as a function of time. And then if we repeat that experiment at different magnetic fields, we would get a data set which looks something like this, where we would be measuring each of the lines in this direction would represent one time trace that we had taken at a particular magnetic field, and then if we add a whole bunch of them together, then we get this complete data set, which is a function of time and magnetic field. Then we can go back later with the computer and just pull out a slice from the data set at a particular time and get the spectrum according to that time. Right? So what you will notice in this spectrum is that this doesn't look very, this is the spectrum actually of an excited triplet state of a porphyrin molecule. This doesn't look like the spectrum that I showed you back here. And there are two reasons for that. The first one is, in order to make our spectrometer fast enough to see this, we have to throw away this field modulation detection that we would otherwise use. So this is, in fact, just the measured absorption spectrum. But we also see emissive signals in the spectrum, because the spin states during the creation of the triplet state get populated selectively. So just to give you an idea of how that works, so if we excite the molecule into its excited singlet state and allow it to relax into the triplet state, the rate of that relaxation into the triplet state is governed by spin orbit coupling. And so the rate of relaxation to the T plus 1, T0, T minus 1 levels of the triplet, those rates are different. And so what we would wind up with is either one of the levels, like the T0, for example, maybe if the rate is faster to that particular level, then we'd wind up with a higher population in the T0 level. On the other hand, we may wind up with higher population, say, in the T plus and T minus levels. Right? And so the selectivity here, it depends on how the triplet is formed. Right? So there are actually two main mechanisms by which you can form a triplet. One is through relaxation from the excited singlet state. On the other hand, I could also, if I've got a neighboring molecule which can accept an electron, I could excite a molecule, have an electron go to a neighboring molecule, and then come back into the triplet state of the original molecule. Right? And so we're actually going to do this talk about this more in the practical on transient EPR. But just to sort of give you a preview of that, if the electron comes back through radical pair recombination, we would get this pattern of intensities where we have absorptive polarization here and emissive over here, and so on, and these peaks in this shape in the middle. On the other hand, if the molecule was relaxing from a excited singlet state, we get this quite different looking pattern. Even though these are calculated spectra, but they're calculated for the same set of parameters for the zero field splitting, same molecule. We're just producing the molecule in two different ways. And we get very, very different spectra. So by using these patterns or analyzing these patterns, you can figure out how the triplet state was created. And so an example of the radical pair recombination occurs in photosystem 2. This is in a very badly damaged photosystem 2 where the electron transfer, which would normally take place to the quinones and so on and lead to water splitting and all of that, almost all of the acceptors and donors and so on have been stripped away here so that all that the electron can do is go partway down the pathway and then come back. Right? And so what you can see here is that we get exactly this pattern and can see that our triplet state was formed by radical pair recombination. I'm going to skip over this here because I'm running out of time. But anyway, I just want to do a little bit of a plug for my own research here. Another thing that you can do with transient EPR is measure the radical pairs themselves directly. And if you have a system which does electron transfer, you can actually measure kinetic rates here. So this is, again, photosystem 1. And you can measure the rate of electron transfer from a quinone to the first iron-sulfur cluster and so on. And these spectra are also spin polarized. Okay, but because we're talking about our people here are interested in bioinorganic systems, we should also touch on briefly what happens with metals which have high spin. Here, if we have a high spin system, usually the zero field splitting is much, much stronger than the interaction with the magnetic field. Right? So unlike our triplet, which I just showed you a minute ago, where here where we have this relatively small splitting, and then when I apply my magnetic field, I have my three levels well separated and so on. And the main interaction here is the one with the field, and this interaction is a small perturbation on it. If I go to a transition metal, usually the relative size of those two interactions is reversed. And here, if we're looking at a spin 3/2 system, we have one pair of levels here, which are plus minus 3/2 and plus minus 1/2 down here. If I apply my magnetic field, the 1/2 levels only split by a small amount compared to this big, big splitting here from the zero field interaction. Okay? And so what we can see in this system then is a transition here at the normal field for the plus minus 1/2 levels, but we have a large shift in the transition between these two levels here. And so in systems like this, we start to see features in our spectrum which are shifted very far away from where the free electron would be. Right? So you can calculate an effective G value for a transition like this. And here this would be, actually I've forgotten what the actual G value is here, but anyway, something like 4, which is very far away from the free electron value, which would be 2. So the way that we can analyze spectra like this is to use what are known as rhombograms. Right? So it turns out that the positions of the features there depend really not on the values of D and E themselves directly, but only on the ratio of E over D, this rhombicity parameter. And so it's possible, if we assume that the zero field splitting is very large compared to the interaction with the field, then we can calculate where all the possible lines in the spectrum would be for any value of E over D. Right? And so I can let my value of E over D vary from 0, which would be an axial system, to 1/3, which is a purely rhombic system, and then plot the various lines that could occur in the spectrum as a function of E over D. Right? And so then, if I have a particular spectrum, I can go and look where am I on this graph and figure out what the rhombicity of the system is. Right? And so these diagrams are referred to as rhombograms. So here's an example which comes from John Goldbeck's lab of the use of this. This is a spin 3/2 iron-sulfur cluster in heliobacteria. And here are some spectra taken at different temperatures. And you can see there are some features at around G equals 2, and then there's a couple of other, there's this broad peak here, but if you look carefully at the temperature dependence, you can see that there is some contribution, which is somewhere around 5.4 on the G factor scale, and another one at about 4.4. So if we then take our rhombogram and say, okay, so where would I expect features at roughly these G values, you can simply move along this axis, and if you get to somewhere around 0.2, then you can see here I've got a feature around 2, one a little bit higher than 2, and I should have some a line or transitions here somewhere around 4.5, and another one here at about 5.5, right? So I can read off basically the rhombicity parameter 0.2 from the rhombogram just by comparing with my spectrum, and I can see that my iron-sulfur cluster, probably not surprisingly, has a relatively high rhombicity. What's more important here, too, though, is the temperature dependent, or what is important. So if we look at our feature at 5.4, if we go down in temperature, it gets stronger. Right? You can see it's somewhat weaker here, and then it gets stronger and stronger. On the other hand, this 4.4 gets weaker and weaker. And so that implies that the feature at this G value is coming from a higher energy state, which has less and less population when we go down in temperature. And that this feature here is coming from a lower energy state, which gets higher and higher population as we go down. And so if our 5.4 G value is coming from this transition and the 4.4 from here, it means that our 3/2, plus minus 3/2 levels must be lower in energy than the plus minus 1/2. And that gives us then the sign of the zero field parameter, or zero field splitting parameter. Okay, I think I'm going to skip over this. This is just an example, another example of a high spin iron. This is now a 5/2 system. What is, if we're in myoglobin, this will give us a G value. There's a very prominent peak at G equals 6 because the heme has relatively high symmetry. So we're in either at or near an axial symmetry situation. And so you can see that we have these transitions in the plus minus 1/2 levels occurring at G equals 6. Another thing that comes about, though, with iron is that in many protein samples, it's really hard to get rid of all of the iron, just in the preparation of the sample, especially if you've got cytochromes or something like that in your organism and so on. So doing the biochemistry, it can be often difficult to get rid of the iron. And so many EPR spectra have a signal which comes from what's in jargon known as junk iron. And this is just iron 3, which is bound somewhere non-specifically, is not really part of your system. And typically the environment that the iron would be in would not have any very high symmetry. And so on our rhombogram scale, we would be over near 1/3 here. And if we look at the where we would expect to see lines, you can see that 3 of these all converge at 4.3. Right? So here's an example of that. And so often in spectra of proteins, there will be an EPR peak at 4.3 just from iron that wasn't removed completely. So if the prep is not as clean as you would like it to be, then often there can be a peak here. Right? And so this is an example from a NADH quinone oxidoreductase, where in this enzyme there's a flavin radical and so on, and the authors who wrote this paper were looking to see if they could find any evidence of an iron, paramagnetic iron species involved in the mechanism and so on. But all they could find was this weak line at 4.3, and by comparing intensities and so forth, we're able to conclude that this is just coming from the junk iron in the sample, that their preparation was not really as clean as they would have liked it. Okay, so we're basically out of time here, so that's where I'm going to finish. What I hope I've been able to show you is some basics of how an EPR experiment is performed. We saw the various interactions that go into an EPR spectrum, so hyperfine, orientation dependence, and so forth. We looked at the G anisotropy, and then took a quick look here at these zero field splitting parameters and how we can use rhombograms. So thank you for listening, and I'll take any questions. Yeah.
To discuss various aspects later on during the tutorials.
Everyone's hungry for lunch.
Yeah. So